All right, today we're going to do 8.1 from the Abeka book, Roots and Radicals. The first thing to be good at this section, you really need to make flashcards and memorize at least through 13 or so on your perfect squares. You could probably get away with getting through about 6 on your perfect cubes as long as you understand the concept that's happening, and you'll figure it out from there. But basically, what we have here is 1 squared, or 1 times 1 is 1, 2 squared is 4, 3 squared is 9, all the way down to 13 squared, or 13 times 13 is 169. 1 cubed, 1 times 1 times 1 is 1. 2 cubed, 2 times 2 times 2 is 8, all the way down to 10 times 10 times 10 is 1,000. I would absolutely make flashcards on those and have those memorized. To be really good at reducing radicals and dealing with them, we need to have those down. All right, so let's talk a little bit about notation. We've worked a lot with exponential notation, which is what we were just talking about. That would be something with an exponent. Pretty straightforward. So if I have something like 2 squared equals 4, that's exponential notation. We also have radical notation. Right, notation is just the way we write something. Radical notation would say something like the square root of 4 equals, it's asking me what number do I multiply by itself to equal 4. The answer is 2, all right? A lot of times we think positive or negative 2, because negative 2 times negative 2 is also 4, all right? But this is called a pure principal root. So when we're just asking the square root of 4, all we're asking for is the principal root, the positive 2. We've learned previously that if you take the square root of both sides of an equation to solve for a variable, then we have to add in the negative. So let's just keep in mind that whenever we see the square root of 4, the square root of anything, it's just asking for the principal root. But if we take the square root of both sides of an equation, we have to do the positive and negative. All right, so on our radical notation, there's some terms you're going to hear me refer to. This part, let's see, I'll just draw an arrow to it. This part is called the radical. All right, that's the symbol. All right, there's an understood index. It's the square root, so there's an understood 2 out here. This guy is called the index. Everything that is under the radical, so this 4 is called the radicand. All right, so every time that we have radical notation, we will have a radical, we will have an index. If it's not a 2, there'll be a number there. If it's the cube root, that would have been a 3. If it's the 4th root, it would have been a 4, so on. We have the radical and we have the radicand. The radicand is everything that's under it. So if it's a quantity, then it's everything that's under there. All right, so you need to know, whenever I say radical, index, and radicand, you need to be able to quickly identify what it is that we're working with. All right, so we talked about the principal root. We won't go into that real deep. Now let's talk about the quotient rule. The quotient, what does quotient mean? Quotient is the answer to a division problem. So if I have something like, let's just look at the actual quotient rule. It's going to be the nth root of A over B. These a lot of times get people because it looks weird compared to what we're used to, but we just have to know n represents some number. Most of the time it's a 2. Most of the time we deal with square roots. But the nth root of A over B, you just have to memorize that if you have a fraction as a radicand, if everything under the radical is a fraction, that means you can break it apart. It would be the nth root of A over the nth root of the square root of B, or the nth root of B. All right, so that's kind of the generic form. That applies to every time that we have actual numbers there. So if we have the square root of, let's do one that works out pretty for now, 4/9. All right, that's the same thing as the square root of 4 over the square root of 9, which is equal to the square root of 4 is 2, the square root of 9 is 3. So the square root of 4/9 reduces or simplifies the square root of 4 over the square root of 9 using the quotient rule, and then that just reduces or simplifies to 2/3. If this could be reduced, we'd still have to reduce it. So what might some of those look like? Let's look at another one. The square root of 49 over 121. This is why I said that I would make flashcards on my perfect squares, because when I look at both of these numbers, I know it's going to break apart into the square root of 49 over the square root of 121. You may already know the answer, but if not, when I go down this list, I'm looking for the number under the radical. It's 49 over here. There it is. 49 is the same thing as 7 squared, so the square root of 49 is just 7 over, go down, 121 is right here. That's the same thing as 11 times 11. So the square root of 49 over 121 is the same thing as 7/11. All right, let's look at one where maybe they throw us off a little bit. They give us a decimal. Let's say they give us the square root of 0.09. All right, we don't like that. That doesn't give us much to work with. This is decimal in a decimal form. I'm going to convert that to a fraction form. All right, so I'm going to write that as a rational number instead of a decimal. I'm going to change it to the square root of 0.09. That would be the same thing as 9 over 100. It's 9/100ths, which is going to, using my quotient rule now, I'm going to break them apart as the square root of 9 over the square root of 100, which is equal to the square root of 9 is 3, the square root of 100 is 10. All right, so what started off as something kind of ugly, we're able to clean it up and make it work out better for us by converting it from decimal notation to rational form, then using the quotient rule to break them apart, and then just finding the perfect square roots of those. All right. Let's look at, do one more. Let's do one with a letter. All right, so let's do the square root of x to the 8th over 4. All right, I'm gonna use my quotient rule first. I've got a radical with a fraction under it. I know I can use my quotient rule and break it apart. That's the same thing as the square root of x to the 8th over the square root of 4. Everybody kind of complains about letters coming into algebra, that we don't want to do math with letters in it, but the letters in this case are actually easier than the numbers. I just have to understand the notation. There's an index, a radicand, and a radical. I need to know what the index is here. And because there's not a number, it's an understood 2. All right? When I have a letter raised to an exponent, the nice part about the letters is all I'm going to do is divide this exponent of the radicand by the index. So that's going to be equal to x to the 8 divided by 2 is 4 over the square root of 4 is 2. All right, so anytime you have a letter under there, all you're going to do is divide. If it's even, you'll divide it by the index of 2, or you'll divide whatever this is by the index that's out there. All right? So that should get us to 8.1. We'll come back and look at 8.2, which is going to be simplifying perfect square factors.